Giglio Power Infrastructure Engineering. In this video, I show how I use COMSOL Multiphysics to model 3 Trefoil cables and ducts in a buried trough and compare results from a full model against a half symmetry model. Here is the full model of 3 Trefoil cable circuits in ducts inside a trough buried 2 meters beneath the surface. All Trefoil cables are identical, and the conductors have a cross-section of 2500 millimeters square, and the insulation is rated for 400 kilovolts. The steady-state ampacity values computed and used in the temperature run of this example were computed by completing an ampacity run, which I have explained how to do in previous videos. The steady-state ampacity value results are shown here: IC1, IC2, IC3 for the center circuit, right side circuit, and left side circuit. Probes were used to measure the maximum conductor temperature on the insulation boundary and measure the maximum sheath temperature. These time-dependent temperature variables were used in temperature-dependent IEC equations to compute the temperature-dependent heat sources, which were used in the heat transfer in solid and fluids physics interface. Here, the heat sources are applied volumetrically to the conductor, insulation and screens, and the sheath. Infinite element domains are applied to the sides and bottom exterior soil domains, and ambient temperature of 40 degrees Celsius is applied to all exterior boundaries. For the surface-to-surface radiation physics interface, all boundaries that bound the fluid are selected, and the opaque and transparent domains are identified and selected. For the laminar flow CFD physics interface, weakly compressible flow selected, include gravities checked. The magnitude and direction for acceleration of gravity is set. A pressure point constraint is applied to one point in each fluid domain. Multiphysics interface nodes are applied to easily and automatically couple heat transfer in solids and fluids with surface-to-surface radiation and with laminar flow. Here is an overview of the mesh with an average element quality of 0.863. Here is a temperature surface plot result of the model at 200 years, where the steady-state ampacity values were used in a temperature run towards the steady state and yielded a maximum conductor temperature of 89.8 degrees Celsius, which is very close to the temperature limit of 90 degrees Celsius. And here's a conductor temperature plot versus time, where we see the conductor temperature starts at 20 degrees and rises towards its maximum. And here's a view in semi-log plot. These maximum conductor temperature results validate the steady-state ampacity values computed with the ampacity run, and it took about 1 hour and 4 minutes to obtain these steady-state results. Here is also a surface and arrow plot of the fluid showing how the fluid moves and induces cooling. Now compare results with a half symmetry model and observe that the maximum conductor temperature also reached 89.8 degrees Celsius, which is identical as the result using the full model. However, using the half symmetry model, the computation time reduced by about 1/3. Setting up a half symmetry model is straightforward and easy. All that needs to be done is remove half the model and apply a symmetry boundary condition, selecting the relevant boundaries for the physics for each physics interface. In a half symmetry model, it is important to scale the heat source and volume of the heat source to maintain the same heat source to volume ratio as in the full model. Here is a plot of the conductor temperature versus time, where the conductor temperature starts at 20 degrees Celsius and rises to the conductor maximum below the temperature limit, just as in the full model. Finally, here is a surface and arrow plot of the fluid velocity, where the results are practically identical as in the full model. This concludes the comparison of the full model with the half symmetry model, and I've shown that using the half symmetry model, we can reduce the computation time by 1/3 and obtain reliable and accurate results just as the full model. Contact Giglio Power Infrastructure Engineering if you would like detailed and fully coupled multi-physics solutions of any power cable system of any complexity. We have novel methods to compute ampacity directly and accurately.